Thank you for coming. I'm Ransom Richardson. I work at Talko. So to introduce myself, I'm going to put up this slide. This has really nothing to do with the talk I'm giving. But this happens to be the last time I gave a conference talk. So this was 16 years ago. I might be a little bit rusty. It's been a long time since I've done this. But the other interesting thing here, I think, is so the title of the talk was about concurrency, right? The concurrent composition of zero-knowledge proofs. Concurrency is something I've been interested in a long time in a bunch of different forms. So about 3 years ago, when we were starting a new company, looking at the technology stack we wanted one that would support the type of concurrency we thought was important in building a service. So this sort of led to, in some ways, into us getting into Erlang. But what I am going to talk about today is Erlang in the cloud. So there are really two key sections to this talk. The first is the idea that the cloud is fundamentally different. So some of you may recognize James Hamilton, who's a VP and Distinguished Engineer on AWS. He has some great talks going into a lot of the technology behind AWS. This is a link to one of them. But he really gets at this idea that the cloud's different. So he covers it from a lot of different aspects. I'm going to look at three aspects that I think are particularly relevant to the service we've built, as well as to people working with Erlang. And those three areas are reliability, deployment, and then dealing with service state. And then sort of the second large section of my talk, I'm going to talk about an architectural change we made to embrace using more Erlang in our service, and why we did that, how we did that. So first, Talko, we're a mobile team communications app. The example I think that makes sense to developers is we use this every day for stand-up. We have a distributed team. We have developers in San Francisco, Seattle, and Boston. This app, often we're mobile. We're not always at our desk. This lets us communicate using voice. Also, we often text on the side. If maybe I stop paying attention partway through stand-up, I miss something, and I want to go back later and hear what that was, I can go back to the recording of our stand-up and listen to that. Or I can easily find where somebody was talking. So that's one way we use it, but we find it really useful in that context. So behind this is our service. Our service does a lot of things. VoIP is key to it, right? So we think voice is key to having effective communication. We have voice traffic going through our service. Our service is all hosted in the cloud. People, I think one concern we had when we were starting out is network performance in the cloud going to be good enough to support real-time service? And the answer, I think, is it's way better than mobile networks. I think particularly there's the latest networks in AWS have enhanced networking. If you're running on a new instance, you get really good network performance, at least good enough that that you can keep up with mobile clients. So we've got our service does a lot of other things. It's a fairly large service. We have a team of 3 people who work on it. We've all worked on clients as well, not full time. And this is the team that does everything from designing the service to implementing and building it, operating it, getting woken up in the middle of the night if we have a problem. So the question is, when we were starting, how are we going to build a big service with a small team? Obviously, developer productivity is key. So there are a few key technologies that helped us do this. First of all is the cloud. We use Amazon Web Services. We use Microsoft Azure. For this talk, I'm really going to focus on Amazon Web Services because that's what most people use. The cloud let us build our service without having to worry about provisioning hardware, building a data center, networking, all that kind of thing. So, second key technology for us is Erlang. Erlang has really made it easy to build code that's scalable and maintainable for us, very reliable. We have, I say it's a big service. We have about 25,000 lines of Erlang code that we wrote, which seems like a really small number. I've worked on projects that have 2 million lines of C++ code, and what we can get done with 25,000 lines of Erlang code is pretty impressive. And so the final key thing for us has been open source technology. We use, for voice processing, we use a modified version of FreeSwitch, but a lot of open source technology. And taken together, this has let us build with a really small team our big products. So the last startup I did, 15 years ago, we were probably at a similar state. We were more than 10 times the size that we were now, just because we were having to build a lot more ourselves. So it's really great. Since open source has been key to us, we've looked for ways to contribute back. The primary library we've contributed to is erlcloud. So if you're using Erlang, if you're using the cloud from Erlang, there's a good chance you're using erlcloud. For us, we started using DynamoDB, which is Amazon's hosted database, shortly after it came out. And there was an Erlang client for it, but it wasn't complete and it didn't meet our needs, so we decided we had to write our own. We decided to write it as part of erlcloud. So we did that. There are a few other things we had to enhance in erlcloud to meet our needs. And when Gleb wanted to hand off maintaining it, he handed off maintaining this library to me, so I maintain it now. But we have a whole bunch of people who contributed to it, so these are some of the other top contributors. And basically, as people are using AWS, they add the APIs that they need to this library. So it tends to be pretty easy. And it's also a great way if you're trying to learn an Amazon service. I understand DynamoDB much better now that I've had to implement every single option on every single method and understand what it does. So if you really want to dive deep into something, implementing an API for us would be great. All right, so I want to talk about reliability. There's, the basic lesson of the cloud is it's unreliable, and I think this should be familiar to Erlang programmers. I mean, we deal with crashes as well, but the cloud is built on commodity hardware. The goal of the cloud is not to build any single instance to a point where it's never going to crash. Instead, you take advantage of the fact that you have a lot of instances to build in reliability. So to a certain extent, you just want to let things crash, right? You have to accept and embrace the fact that in the cloud, things aren't going to crash. They're not going to go well at times. And in Erlang, we have a similar thing, right? We have processes and we have supervisors. So if your process crashes, your supervisor will restart it. In AWS, you have instances. If your instance crashes, you can use an auto-scaling group to restart it. Now, Garrett was just talking about naming and the importance of good names. This thing, autoscale group, is pretty poorly named because it doesn't necessarily have anything to do with scaling. So the simplest way to use an autoscale group is to say, I always want to have 2 instances of this type up and make sure I always have 2. And it will never change. It will never scale, but it'll be there watching. If one of those instances goes down, it'll automatically start another one for you. So that's key to building a reliable architecture in AWS. Unfortunately, so in Erlang, if your process crashes, your supervisor will typically restart it very, very quickly. In the cloud, it takes minutes, probably. It takes a while for the autoscale group to realize that it's down and then start up a new one. So it's not quite as easy to recover immediately from crashes in the cloud as it is in Erlang. A couple more key ideas in AWS in particular in terms of reliability. First of all, if one instance is going to crash, you have to have another instance there that's going to be able to do whatever it was doing. Once you have more than one instance, you have to make sure that the instances you have are not going to crash at the same time. Now, the way that you do this in Amazon Web Services is you make sure they're in different availability zones. And the concept of availability zones is so you have regions, which are geographical regions. So you have US East, which is in Virginia, US West, EU West in Ireland. So those are totally separate, and they have relatively high latency due to speed of light between them. So certain services, you really want to have low latency connections, but you still want that protection from failure, and that's where availability zones come in. So availability zones are located close enough together that communication latency is very low between them, so 1 or 2 milliseconds. But they're far enough apart that it's really unlikely that a single natural disaster or man-made disaster will cause them to fail at the same time. So they do things like make sure they're in different floodplains and all kinds of things like that, but they're close enough that you can still have low latency communication between them. So you need more than one instance. You need them in different availability zones. You have to have extra capacity, right? If you have 2 instances, but they're both at 90% capacity and one goes down, you're not going to be able to absorb that on your other instance. And it's also possible, you know, if one instance goes down and then that causes, in our case, we're handling a lot of connections. If those connections going to the other instance, even if you had enough capacity to handle them at steady state, there's extra work to do to set up those connections. So you have to be able to absorb that work. So here's sort of a simplified view of our architecture. We have clients that connect to our service. So we have 3 types of servers in our service. We have media servers. So media servers run FreeSwitch, you know, our modified FreeSwitch, as well as Erlang code that we have that you know, controls the conference, handles recordings, and things like that. But effectively, that is real-time traffic, right? So that's UTP and RTP traffic. Our clients also connect to our session servers. So this is a long-lived connection. If it's a web client, it's over WebSockets. Mobile client is SSL. And this is our own, on top of that, we've built our own protocol that's a synchronization-based protocol. So, you know, mobile clients are on unreliable networks and typically often slow networks. We want to make sure that for our clients to connect and synchronize their state, it's not too expensive, right? We're not pulling down the full client state every time. So we have a synchronization state where basically the mobile client will send a high water mark or a set of high water marks, and the service will then go check our storage and see has anything changed since the last time you connected. So, but then once that state is established and we have this connection, then we're only sending anything that changes down to the clients. And finally, we have what we call our BZ servers. This, I guess, is a placeholder name if you were at Garrett's talk. It has no meaning and intentionally no meaning. This was, you know, failure to find the right word, so we went with a word that meant nothing. But basically what they do is they provide the interconnections between our different services. So client is connected to one session service, needs to talk to a client on a different session service. That communication will go through the BZ service. So in terms of reliability, what's going on here, though, is that each of these types of servers, we have multiple instances. They all have their own autoscale group. They all have instances in different availability zones. And then finally, our storage backend, we use hosted storage that is reliable without us having to do much. So when we look, the other piece to reliability is getting reliable on our instances. So we've got our service running in the Erlang VM. But when we were first doing this, we were worried, well, what if the Erlang VM crashes, right? How are we going to restart that? So there's this project, open source project, ErlD, which is makes the Erlang VM look like a Unix daemon. So that, and it does heartbeats into the VM, makes sure the VM is still alive. So it's watching the Erlang VM. If the Erlang VM crashes or hangs, it'll restart it for us. On top of that, we have Upstart, which will restart ErlD if ErlD happens to crash. And you know, that will start up when the instance reboots. So if the instance reboots, everything starts. If the Erlang VM crashes, it restarts. It turns out, I think, maybe we over-engineered this a little bit. I don't know that you necessarily need to go quite this far. The Erlang VM really has not crashed very much at all for us, certainly recently. So the fact is that our auto-scaling group, and actually working with the Elastic Load Balancer, are probing the Talko service and periodically, you know, regularly making sure the Talko service is running. If the Erlang VM did crash, you know, it would, I think, be acceptable for our application to just let the Erlang VM crash. The autoscale group would realize our service is down and restart a new one for us. So if I was doing this again, I might not build all these layers, but erld does work pretty well if for some reason you're worried about the Erlang VM crashing. All right, so that's a little bit about reliability. Deployment in the cloud can also be different, and it doesn't have to be. There are two approaches. A lot of people do what you typically do with your own data center, which is you've got your instances running and you upgrade, you deploy your new code to those instances. The other approach, though, that the cloud enables that would be a lot harder in your own data center is you just deploy all new instances. So the cloud has effectively infinite capacity. So if you want to run twice as many or 3 times as many instances for a short period of time, that's something you can do. And this enables you to deploy your service in different ways. And that has some advantages. First of all, it's easy to roll back. Right? So you start deploying your new code, you realize there's a problem, you still have all your old instances running. They're still there, ready to take load back. The other thing is, as we talked with reliability, your instances can crash and you need to restart instances from scratch all the time to be reliable. If you're restarting instances from scratch all the time, every time you deploy new code, you're testing that constantly. The other thing is if you have an instance that if your instance is up for a few hours or a few days, there's less time for somebody to get on that instance and change some configuration that's keeping things running or introduce some bug or something else. Your deployment process is very repeatable, and you know how your instances are. And also, you have less of a security attack surface area because your instances are constantly cycling. You're always taking down the old ones, you're always putting up new ones. It gives attackers less time to actually find your instances and get into them. So one way people talk about this is blue-green deployment. This is a diagram from Martin Fowler's blog. But the basic idea is, hey, you've got your service running, you've got the blue service running to start with. Then you deploy the green version of your service. So you deploy your service all new. Green version, once you think green is up and good, you switch the router, and that's where this diagram is. The router is now pointing at the green service. And then once you're sure that's working, you can take the blue service down. This sounds okay in practice. I think when you start looking at the details, it gets kind of tricky. So this diagram, I look at this diagram, and so it's deploying the whole service, and this is kind of a typical 3-tier web application database server. I don't really know how you deploy a whole new version of your database. How do you migrate the data to the new version? How do you roll back if there's a problem with the new version, right? That seems really hard. So that's definitely not something we do. I mean, we use hosted databases, so it's not something we have to do. But the other thing here is that this shows doing your web tier and your application tier at the same time. So effectively, you deploy your whole service at once. And if you've heard of microservices, there's sort of a trend in the industry, or at least a lot of buzz around the idea that you want to keep your services separate and upgrade them separately and reduce this kind of coupling. So I think in practice, this is kind of an inspiration for a way to do deployment, but in practice, I think people do it differently. Netflix is well known for both doing this type of deployment. They call it red-black deployment, which I think fits better with their corporate color scheme. But I think they also do microservices, and they deploy each service individually, as do we. So what we do when we deploy is that we deploy each service individually. So we can upgrade our media servers without doing anything else. The disadvantage of doing that, of course, is that we need to maintain backwards compatibility. So if we're changing the protocol, we need to support both while we're doing the deployment. It makes the deployment a little trickier than if we could just do an immediate switchover. But the other problem for us is that we've got state, right? So we've got FreeSwitch there, which is running an audio conference. There are a bunch of people connected to it. If we lose that box, users are going to notice. It's not horrible. It's probably, you might have a few second interruption in your call. So not the end of the world, but not what we want to do based on our everyday deployment. So what we do is we deploy our new instances, we test them, make sure they're running, and in particular, everybody internal to the company runs a special build that always connects to the newest instances. So while our customers are still on the old instances, we're all running the newest stuff that's out there. We can test it. Depending on how big the changes are, we might test it for a long period of time or a short period of time. But once we're pretty sure that it's stable and good, then we close the old instances to new traffic. So we basically say no new traffic is going to go to the old instances. Any new calls will start on the new instances. Then we wait for the load to move, and sometimes we're watching. There's like 3 hours later, there's one call with 10 people in it, and we're like, someone's in a really big conference call. But we wait for them to finish, and then we'll take those instances down. So that's kind of how we do deployment. It's a little different for each of our services. So like I said, media services, we have to wait for the calls to finish. Session services, often the clients have long-lived connections. We typically don't wait for all of the connections to close, and we'll move some traffic over and make sure our metrics look good. And then we'll just bring the old ones down, and we have a bunch of connections go at once. The BZ services, which are the interconnection, we haven't implemented this as well yet. So what's going on there is that we have a hash ring that allocates objects to those services. When we deploy new ones, they start getting traffic right away. So at some point, I would love to have something that lets us sort of more gradually move traffic onto those, but it's not something we've gotten to. So service state ties in with those last two topics, right? Reliability, you need to expect your instances to go away and bring new instances up. When you're doing deployment, one way to deploy is to bring up new instances. That gets hard if you start having a lot of service state. So in the cloud, there's a lot of pressure, or if you take an Amazon course on how to architect for the cloud or go to their talks, they're really pushing you to build stateless services, right? So you build a stateless service, basically your service code won't store state there. It'll get whatever state it needs to process an event from a different data store or other places. This makes it really easy to build reliable and deployable code because if you need, or scalable as well, right? If you need more processing, you allocate more instances. You don't have to worry about migrating state or anything like that. The problem is there's lots of stuff you can't do without any state. And so in the Erlang world, I think when I think of service, I think of gen server, right? And a gen server has code that runs on the state in the server. And it's actually really great. Like, this is why the actor model is so great, or this is the actor model, right? You have your code, and you've got a single actor on it, and you can easily reason about that state, that system, and understand what's going on. But in some ways, it makes it harder to build in sort of the cloud a reliable and scalable service. But with Talko, to support really low latency communication between clients, we needed to embrace the fact that we have some state. We have these calls that are in progress. We have persistent connections from our clients, this synchronization state. We don't want to be constantly having the clients reconnect. And we have state on where every client is connected so that we can reach them if somebody wants to send them a message. So the question for us when we were building our service is, how are we going to manage this state so that we can build our service, but still make it reliable and deployable in the cloud? And what we end up doing, and the way I think about our solution is that we think of this state as ephemeral, right? Like a cache in some ways. So we're not going to be too concerned about losing it. We don't want to lose it all the time, but we're not going to add redundancy. We're not going to really try to avoid losing it. Instead, we're going to embrace that it can be lost and make sure that we can recover from losing it quickly. What that means for our different servers is kind of different. On the media server, if we lose state, we lose your in-progress call. Session server, we lose your state. Your client has to reconnect to another server, reestablish synchronization context. You might, probably that one a user wouldn't even notice. If we lose one of our BZ servers that provides the interconnect, there could be some messages bound for you that you miss, and then you'll have to notice based on our synchronization protocol that you missed something and pick it up. So, there could be a little bit of flakiness, but probably not something that users are going to pick up on. It does have challenges. You know, the way we build things with ephemeral state, obviously, user impact if it gets lost. It's required that we can detect and heal outages very quickly. So if a server does go down and we start losing state, we need to know that very soon. We found that we're at about 10 seconds now that it'll take us to realize a machine is down. We don't want to tune that down too far because we start getting false positives if it's, you know, there's some just blip in the network or something like that. But we want to be able to notice, hey, this machine hasn't responded for 10 seconds and it's time to assume it's gone. So that's been a challenge for us. It takes some time for load to shift to new instances, depending on, you know, if we deploy new media instances, they aren't going to be doing anything for a while until there are a bunch of new calls. So if we have all of a sudden our service overloading, we can't just deploy a bunch of new instances. It's going to take a little while for load to distribute there. And finally, if you lose the state, like if we lose a synchronization context, it may be more expensive to reestablish that. So when we were doing the scale testing on our service, we tested both, you know, how many steady state connections can we handle, how many clients can we handle, but also what's our rate of accepting new connections, because when an instance goes down, we're going to have a lot of reconnects, and we needed to make sure we could handle that spike. So that's sort of the end of the first cloud is a different part of my talk. Talking about reliability, deployment, and state. So I'm gonna build a little more on that state thing, and after having this we built this service. We launched Talko about 6 months ago. We went public, and all of a sudden we had orders of magnitude more users, right? So we'd been planning for this, preparing for it, you know, wondering what's going to happen, and it really went smoothly, right? Our Erlang code scaled up fine. Our service scaled up fine. Everything was going great, right? So of course, if everything's going great when you launch your service, it's time to change the architecture. So our original architecture, we didn't have our BZ server. We were using Redis as the interconnect for our servers. And if you're not familiar with Redis, I've heard it referred to as a data structure server. People use it for a lot of different things. You can use it as a cache. You can use it for more persistent data. You can make it redundant. We were using it in a pretty simple way to provide interconnects between our different services. So you know, basically it has built-in support for pub subs. So if you're in a Talko call, you would connect to your session server. Your session server would subscribe to you to a pub sub channel for everybody interested in that call. And then any changes would go over that pub sub channel to you. And we'd also keep ephemeral state there. And as an example of the kind of ephemeral state we kept, I'm going to briefly introduce user awareness. So when you're in a Talko call, you've got a bar across the top of your screen that shows who else is in this call. So people who have access to the call but are not in the call are grayed out, you know, in black and white. If somebody's in the call, their picture's in color. If somebody's typing in the call, if they're texting, they have a blue halo around them while they're texting. If their mic's open, they have a green halo. But basically, this is state that we need to update very frequently, like every time you start and stop typing. So it's not something we want to put in persistent storage. But and it's ephemeral, right? It's the clients are constantly sending pings to the server saying, "Hey, I'm still here," and we can use those to regenerate this information if we need to. So it fits into the definition I'm using of ephemeral state in that if we lose it, it'll get regenerated within 30 seconds. So how we implemented this using Redis, actually the hard part of implementing this using Redis is, okay, everything's going fine. We've got 4 clients connected. I have four clients up there. That's to represent the user awareness state. So we're aware of all 4 clients. You know, so what happens when a client goes away, right? They lose their connection, the app crashes, something happens, they're no longer there. But they didn't go down in a graceful way. They didn't tell us I'm no longer there. Well, this is pretty easy, right? They're connected to one of our session servers, and it can realize, hey, this client's gone. I haven't heard from them for a while, or the connection went down. So this session server can tell Redis or update the data in Redis, take this guy out, and then tell all the other session servers who are interested in this, hey, this changed, there's new information, go tell your other clients. So that's pretty easy. It gets a little harder when the actual session server goes down, right? So now these two clients are no longer connected to our service, but who's watching this? Who notices that this session server go down? Well, right, it's not an impossible problem. We've got a bunch of other session servers. But so one of these guys will notice, hey, he's gone, and we'll pick this up. So not a real hard problem, but gee, wouldn't it be much easier if we had a gen server that was responsible for this? So that instead of having some distributed protocol where any one of many processes distributed throughout our application needs to be watching for this kind of failure and do this kind of fix-up on our state so that we can get rid of the lost clients. We really, after doing a lot of Erlang programming, realized, this fits the actor model. We really want an actor who's responsible for this state. This is actually a fairly easy problem to solve, but it was also an easy problem to explain. There were a number of other sort of related but a little more complex problems that were hard to do in a distributed manner, right? So using Redis, and Redis, was a data server, so it had the state, but it didn't have code. So it really fit in that sort of more stateless model where your state is separated from your code. It made it hard for us to do this. So, we were doing things like, well, you've got lots of systems that maybe are updating the state at the same time, so you need a transaction. And taking out a transaction on a distributed system, you're blocking the connection in Redis while it's going on. So a bunch of these issues, and we said we can really simplify our code if we were to have an actor. So that was what drove us to say we're going to use more Erlang. We're going to replace our Redis server with what we called the BZ server. So we replaced it with an Erlang server. It has a gen server per shared object, so there's a gen server for the call. It's sitting there watching, and it wakes up on a timer and says, oh, is there a client that hasn't pinged in a while? And if so, we'll automatically remove them. So that made that easy for us. And that example of how do we realize that one of our servers crashed and who's responsible for doing the cleanup. Now we had somebody who's responsible for doing the cleanup. And the surprising thing here, so when we were cutting over, obviously we had to keep our service up while we were making this big architectural change. So for a while we were running both architectures. Effectively we had the Redis server up, and as we started moving functionality over to our Erlang server, we were exercising both code paths. So our data would come through, it would come through Redis and it would come through Erlang, and we would actually get the data faster consistently through the Erlang server than the Redis server. This was surprising to me because Redis is single-threaded C code that's supposedly really fast network. So yay Erlang. I'm not sure it's a fair comparison. I didn't actually dig deeper into it. It could be that the Erlang Redis client library is kind of slow, and it really wasn't the server, but it was a good sign that the Erlang server was faster. So that's the end of that section of the talk. So these ideas of state, reliability, durability is also something that Amazon is thinking a lot about. And one of, I think, the interesting things they're doing and coming out with is this service called AWS Lambda. It's not a service we use, and it's not one that I think is going to solve problems for us, so I'm not interested in it in the practical sense at this time, although I do see some applications for it. But I think it's interesting from the sense of where is the cloud going. And the idea behind Lambda is you write a function, so you write a JavaScript function, and you send it to Amazon, and you tell them when they should run it. So maybe if a new object gets uploaded to your S3 bucket, hook it up to your Lambda function. Your Lambda function will run, and whatever output from it will get stored wherever you want to store that output. So you could use it for audio transcoding. Anytime somebody uploads a new audio file, run my function, I'm going to transcode it, I'll store it back in S3. But there are lots of other things you could theoretically do with it. If you're able to boil your code down into a stateless function then you don't have to worry about any of the things I've been talking about, right? You don't have to worry about reliability and deployability because they'll handle it for you. So, so I think it's interesting to sort of think about, you know, well, what does this enable from a service standpoint, right? As somebody who's responsible for operations, I would love to be able to write a service without having to worry about the actual instances. So I have a question before I let you guys start with questions. One thing we haven't used is distributed Erlang. We haven't used distributed Erlang in the cloud. I don't know if we should use it. It's something I ponder if this would have made things easier for us. We were concerned about it when we started with Erlang, you know, coming new to the language. We didn't want to, we wanted to hedge our bets a little bit on how easy it would be for us to switch to other technologies, so we didn't want to go here. But we had other concerns that, you know, certainly if, you know, would distributed Erlang work well across availability zones, or as we scale out to multiple regions, how would it work across regions? We, you know, as I talked about, we're really sensitive to how quickly we can detect failures in our networking stack, and we didn't know would distributed Erlang work well enough for us there. Plus, we were worried about the full interconnection and how that would scale. So I wish I could say something really interesting about this because I think it's an interesting topic, but I have no experience. So if you do, I would be interested in hearing about it. And that went reasonably quickly, so hopefully you have a lot of good questions. Yeah.
Do you do anything chaos monkey style to check your failover and load balancing?
Yeah, so the question is, do we do anything like Chaos Monkey? So probably most of you are aware of it. Chaos Monkey is a Netflix originated project that will randomly kill your instances. No, we don't. It's not something we've had time to set up. I think it's valuable. So, you know, we do it during our deployment process, and particularly, so what I described is sort of our ideal steady state deployment process. Certainly in our development environment, we're often much more brutal about what we do. And we've certainly done it by hand a number of times where we'll kill an instance and make sure it recovers, but we have not automated that. Limited time, I think it would be valuable. In the back? Yeah, you. Yes, you. We looked at it enough. I mean, I think the other concern we had was around security too. We dug into it a little bit, but not to the point where I feel like I can answer those questions. So, you know, I didn't look at what are the algorithms for how it detects when a node goes down, for example, which I think would be really interesting to know. I do know, so in Fred's book, in Learn Use Some Erlang, he mentions about distributed Erlang that it tends to assume that failures are hardware failures as opposed to net splits, which is something I'd have a little bit of concern with in the cloud. I think you're much more likely in the cloud, you know, to have a net split between your AZs or some other things like that. But I don't know what the code looks like, and I don't know what the algorithms are, so I'm speaking from other people's experience. Yeah, Dimitri.
It's not a secret. What kind of inbound and outbound traffic do you guys have? Like the order?
So I don't want to speak to sort of exact numbers. It's relatively small, and I think you know our you know, I'll say, so our session servers, for example, we've load tested and scale tested, and it's certainly that a single server for us on a moderate-sized EC2 instance can handle hundreds of thousands of connections of clients. So, you know, we're a relatively new startup. We're not at huge scale yet, and our Erlang instances handle a ton of stuff, so we're not running a ton of instances. Yeah, I don't know if that, you know, in terms of actual. Yeah. I don't have good numbers on traffic or breakdown between real time and you know, photo uploads and other things. I don't have that data. Sorry. Yeah.
You mentioned you use the deploy new strategy. How often do you do new deploys? How often do you put new code out?
It depends. I mean, so we're a small team, so it depends what we're working on. We've certainly on a bad
times a day or once a year?
on a bad day when we deploy some bugs, we'll do 12 deploys a day just to fix things. I mean, hopefully that's in our development environment.
These are all new deployments. You don't patch something small. You don't
No,
have any of them.
no patching. It takes us about, from code check-in to having that code running in new instances in our development environment is about 5 minutes. So it's a pretty quick turnaround. What? Yeah. Yeah, I mean, a couple things there. So the way we do it is most of what we have is baked into our AMI. So all our dependencies are baked into the image that we're booting. And then our build, we actually store in S3, so we just tar up all the Erlang stuff, pull that down, expand that, and get it running. So it boots up pretty fast. Our times are a lot faster since we switched to the new EBS volumes that are SSD based. Those boot up a lot faster. And actually, we made that switch at the same time we switched to VPC. So one of those switches resulted in us booting up really faster. I'm not sure which one. I'm guessing it's the drives. I will say, a little digression, that you have to be pretty careful with the GP2 drives. The one outage we've had has been caused by that. But basically what happens is the GP2 drive, so it's SSD backed EBS, so off instance storage, and they have a quota on how many operations you can do. If you accidentally hit that quota, things start behaving really weird. And there's not even a good, at this point they're going to add one, but there's not even a good metric that shows you've hit your quota. What happened to us was we were switching to use a different log host, upload our logs to a different host, and we switched. We accidentally, so we were switching how we were collecting logs. We accidentally started putting those to EBS instead of to instance store. And after a while of our logs going to EBS, we hit that throughput. And what happened at that point was that any Erlang process that tried to log would hang for an indeterminate period of time. But any Erlang process that was not logging, including the ones we were using to heartbeat and make sure everything was running, would continue to run fine. So it was an interesting failure mode. So anyway, if you do, those drives boot really fast. Be careful if you're using them that you're not writing too much to them. Yeah, I mean, well, so we have a dialyzer. That's surprising. I mean, we build a lot into the PLT, and then our dialyzer run is 10 seconds, 15 seconds. So
Or she's using half the Amazon cloud.
no, that's yeah, single instance. So another question.
So when a connection drops, like how does it know which server to connect to, or how do you do routing? Is it like
Okay, so routing's interesting. Let me bring up the. There's not an easy answer, and it depends on which server. So. Well, let me actually. So there are 3 different servers. So our session servers, effectively what the clients will do is always try to connect to the last one they connected to. If that doesn't work, they actually go through our Elastic load balancer with an HTTP request, and then we have code which picks a session server for them. So they'll then reconnect directly to that session server. If a media, effectively when you enter a call, you're telling the session server, I just entered that call, and that session server will pick a media server for you and assign you to that media server. The BZ servers, which are the interconnects, that's a little more complicated. That's a hash ring with consistent hashing that assigns objects to individual servers in that group.
I was just curious, so you built a lot of patching. Is there a reason that you're not using cloud upgrades, or you've got a stateful system?
Yeah, I mean, so basically we thought the advantages here of doing new deployments, making sure we always knew what state our instances are in, the fact that we needed to be able to deploy quickly anyway, were outweighed the downsides. And in particular, I think hot patching is something that I looked at and thought that looks really complicated to get right. To write a bunch of code that's going to correctly mutate the state. It's hard enough to get the rest of your code right without worrying about how to, we already have to do enough backwards compatibility between our different services that trying to get backwards compatibility right within a service was something we didn't want to bite off. So it's useful sometimes when we're debugging something, we want to change the code we're running, or in the development process, it's we'll load a new version of the model, but of the module, but we've never done a app upgrade. Yeah.
How do you decide which region to send traffic to?
Right now we have one region, so it's an easy answer. It's something we've looked into. So I think the way we'll do it is you can use Route 53, the Amazon DNS you can use to do location-aware routing. So it will decide what region is closest of the ones you support. So I think we're going to take advantage of that feature and use that to decide where to send clients, but not something that we've dealt with yet.
So when you spoke about the BG server, you mentioned Gen server, and as what I understood was you use the BG server to restart your other server. Is there a reason you didn't use supervisors, or you do use supervisors?
Yeah, so the question's around the BZ server and kind of what exactly that's doing. So it's not exactly watching the others, restarting the other servers, but it's noticing when clients change, state changes when different clients connect, and what's going on. So actually restarting the servers happens through the autoscale group in Amazon if the server crashes. Great. Thank you all.